So good morning and welcome to Classical Mechanics 1 at CMI. This is our fourth lecture on Friday, the 12th of August, 2022. So before we get started, are there any questions? I hope I'm audible.
Yes, sir, you're audible.
Okay, thank you. One thing is that the problem set 1 is only partly graded. So in case you have received some semi-marked answer sheets, please hold on. They will be completed and then you will be informed. Any case, I hope you have had a reasonable first 10 days or so at CMI. I have enlisted the help of some teaching assistants who who will also be a source of help to you when needed. I will share their names. Yeah, and I am thinking of dividing the batch into groups who would be able to, and each group will be assigned one TA to direct any inquiries. Okay, so if you have any questions, you're welcome to ask now. Otherwise, we will continue. Okay. Yeah, so our TAs for this course are Ankit Yadav, Priti Sinha, then we have Pankaj Saini, and then there's Shubhendu Prasad Mandal. We also have Ripunjay Dwivedi, Siddhant Shah, and Advik Jagannathan. So these 7 people will help us. Yeah, was there a question? Okay, so I will share their information with you. So towards the end of the last discussion yesterday, we spoke about the position of a particle, the location of a particle as a point in space at a given instant of time. And of course, it could be at various locations, and all those are points. And you could have that collection of points. Those points can be given names like here, there, and everywhere, and so on, or ABC, or whatever way you want to name them. At the end of the day, they're just some points. And of course, the dynamics involves motion from one point to another. Yeah, so let us discuss this in a little bit more detail. Yeah, and of course, giving an address to any of those locations needed a coordinate system, and we spoke a little bit about that. We will say more about that now. But the main point was that the location of a particle is not a vector. It is not physically associated to any direction or any intrinsic notion of an origin or length. But for our convenience, when we study motion in three-dimensional Euclidean space, it is convenient to regard the position of a particle, location of a particle as a vector relative to some specifically chosen origin and coordinate frame. Okay. Yeah, so now the infinitesimal displacement of a particle, so that is simply its location so far. The infinitesimal displacement of a particle over a time t to t plus delta t does define a vector, albeit a vector with infinitesimal length. Okay, so we can call this vector delta r at the time t, which is defined as r of t plus delta t minus r of t. So that is an infinitesimal displacement over a short duration, delta r. Yeah, so this was r of t and this is r of t plus delta t. Yeah, so now the concept of infinitesimal displacement does define a notion of origin, namely the initial location of the particle at time t. Okay, so that is a physically well-defined concept, the initial location, so that you can choose as the origin. And the infinitesimal displacement vector then points from this origin to the location of the particle at time t plus delta t. All right, so you see how an infinitesimal displacement automatically defines a vector for you. It comes with an origin, it comes with a direction, it comes with a little arrow, which way it's moving. So all the concept of a vector are encoded here, are used over here, unlike in the notion of a location alone. However, the concept of an infinitesimal displacement does not define a coordinate frame, right? It does define a vector. So that is a sense in which a vector can be a physical concept, a geometric concept, but a coordinate frame is an additional appendage that we put for our convenience. So the infinitesimal displacement only defines an origin and a vector delta r. However, we may resolve delta r along the axis of any frame of our choosing. So here we will, for convenience, parallel transport. So we will choose some frame, pre-specified frame with some origin O. Particle may have been here at time t and then t plus delta t. There is some delta r here. We will parallel translate that delta r to the origin just for our convenience. So that it is a vector that emanates from the origin of our coordinate system, Cartesian frame. And its components with respect to this frame, yeah, we can resolve it. That is, we will drop a perpendicular to the three axes and get the three coordinates. That delta r is then resolved as a vector with respect to this origin O, and the components are written as x of t plus delta t minus x of t, y of t plus delta t minus y of t, and z of t plus delta t minus z of t. So this is how we get the Cartesian components of the displacement vector. Yeah. Okay. Now, the arbitrarily chosen origin of the Cartesian coordinate system xyz has no physical relevance to the infinitesimal displacement vector, right? I mean, we simply arbitrarily chose some origin and chose some orientation of this frame. I could very well have chosen a different origin and a different orientation. It would be equally valid. So we see that that's not given by the particle's motion. It is something we choose. And moreover, we have parallel transported this displacement vector to the origin for ease of some calculations, not because it is intrinsically present. Okay, so I hope this very fundamental concept is entering into your understanding. Now, as we have said before, the velocity of the particle is defined as the limiting value of the difference quotient. So by difference quotient, I mean r of t plus delta t minus r of t. Of course, these are both vectors. So the difference of these two vectors divided by the difference in time. And then you take a limit as delta t goes to 0. So it's the limit of the differential quotient. And this is how the notion of a derivative arose.
Sir, why partial derivative?
No, I have not mentioned any partial derivative. Yeah, so I simply introduced a symbol delta r to denote any small change in r. Okay, so there is nothing partial or full or anything about this. It is simply the difference in vectors at two instants of time. And to further elaborate, r, which I said is the position vector of the particle, is a function only of one variable, which is time. Yeah, so we are simply computing the time derivative of a function of one variable. So in that sense, there is no meaning to partial differentiation, so to speak. There's just one derivative with respect to time. So if you like, you can write v of t as dr dt. There is no partial differentiation here. Partial derivatives arise when you have functions of several variables. Okay. So sorry, who was asking that? Who asked that?
Me, sir. Ryan.
Ryan Hota. Okay. Have you finished? I hope your medical trip yesterday was satisfactory.
Yeah, it was.
Okay. Yeah. So I mean, is it clear why this is not partial differentiation?
Yes. I mean, yeah. Okay. Yeah.
All right. All right. So, I mean, the appearance of this symbol delta does not have any particular significance. It's just conventional to use delta for small things. That's all. Yeah.
But does the triangular symbol delta have any particular significance?
Oh, you mean to use this symbol, capital delta?
Yes. Yes.
Yeah. I could very well have used capital delta r of t divided by capital delta t. Yeah, if I was so inclined, there is no difference. It is just a notation that I got used to. That's all. Some people will use capital delta, some people use small delta. But I hope you are aware that this one is small delta and this is a capital letter. That is the only difference. As we go, we will pick up the Greek vocabulary, sorry, the Greek alphabet. Okay, now the velocity of the particle is of course a vector. It is the time derivative of the position along the trajectory. Yeah, and we already wrote this formula for it. So now we may ask, where is this vector emanating from? And we would like to think of this as defining a vector that points from the instantaneous location of the particle in the direction of motion. Okay, after all, it is the tangent vector to the curve, geometrically speaking. So it is most natural to regard it as a vector that emanates from the instantaneous location of the particle and points in the direction of motion at that instant. Now, as I said, it is a tangent vector to the trajectory, and its magnitude has a special name. Its magnitude is called the instantaneous speed of the particle. Okay, so this small v, which is magnitude of v vector, is the speed of the particle at time t. Okay. Yeah. Now, the origin from which the velocity vector points moves with the particle. Okay. So this is an example of a vector whose origin moves with time. So we have to now get used to that. There may be vectors for which it is convenient to view the origin itself as moving. However, for many purposes, it is convenient to resolve V along the Cartesian coordinate axis, which we had pre-specified, just some kind of convenient choice. Yeah, by moving the origin of the Cartesian frame to the current location of the particle. Okay, so the origin of the Cartesian frame was somewhere else, but we will at each instant of time, for the purposes of resolving the velocity vector, we will move it to the current location of the particle. Then we will identify the Cartesian components of velocity with respect to that frame. And that is very convenient for our calculations and visualization. Yeah, so what we were saying is that with this understanding, the velocity vector may be written as a ordered triple of components x dot, y dot, and z dot. Yeah, each of course at that time t, and also written in vector notation as x dot x hat plus y dot y hat plus z dot z hat. Okay, so x of t, y of t, z of t was the address of my particle, the Cartesian coordinates of my particle, and upon that itself, you may or may not want to regard as a vector, but certainly once you differentiate it, you do want to regard it as a vector. It is the velocity vector. Okay, now so far I hope you are with me. The next, the time derivative of the velocity is called the acceleration, which may be viewed.
Sir, could you again explain that point, that origin from which the velocity vector points moves with the particle, that point?
Yes, yes. So may I know who spoke?
Ankon.
Ankon Mukherjee. Am I right? Yeah, yes. Yes, so the point is that we agree that we are studying a particle that's moving. So it's here now, it's here tomorrow, and there day after. And at wherever it is currently located, there is the instantaneous direction in which it is moving. That helps you to define this velocity vector. But we also notice that the velocity vector, if we regard it as emanating from the current location of the particle, that point changes with time. Okay, so this is the basic observation. Therefore, we say that the velocity vector defines for us an origin, namely the location of the particle. But since that location of the particle is changing with time, the origin defined by the velocity vector changes with time. Okay, that's all we are saying.
Oh, so you are changing the origin with the location of the particle.
Yeah. So what I said up to now concerns only the origin. Okay. So far, I mean, in the past two sentences, it's only about the origin. Furthermore, if you want to resolve this vector into components, okay, often we like to work with components, XYZ components. For that purpose, what should we do? After all, this is some vector located here. My origin of that fixed frame is somewhere else. It doesn't coincide with the origin defined by the velocity vector. So to remedy this situation and resolve V along these axes, I will move my axis, my fixed axis, with fixed origin to the current location of the particle. So I parallel transport it here at the instant considered. Right, I'm considering the situation today now. Yeah, so I'm going to move it there, and then once I have moved it, I know how to resolve it into components, right? Because we know how to resolve a vector into components, provided the origin of that vector coincides with the origin of the coordinate system. I mean, that is how we have defined things. This is my vector. I make a orthogonal projection onto the three axes. Yeah. So it is for this purpose that we want to move our fixed frame with certain origin that is always fixed to the current location of the particle for the purposes of resolving the velocity vector. Yeah. I am only saying in somewhat careful terms things that you may already be doing without a second thought. Yeah. In any case, Onkon, are you satisfied with my response?
Yeah.
Oh, okay, yeah. I mean, if you don't like all this, then one can take a very pragmatic view. Position of particle is defined by these three numbers. Simply differentiate it. You get some three numbers. You define them as the components of some vector called velocity. Forget
Yeah.
everything else. All right, you can just
Mhm.
proceed like that.
Mhm.
That's okay for calculations, but for a deeper understanding, we need to know what we are doing. Okay. But that was a good question you raised. Now, I of course said that if you take this vector, velocity vector, and now go and differentiate that once again, you will get the acceleration. So that again is regarded as a vector with the three components in the x hat, y hat, and z hat directions, whose the coefficients or the components are x double dot, y double dot, and z double dot. So needless to say, the acceleration is the limit of the difference quotient v of t plus delta t minus v of t divided by delta t as delta t goes to 0. And I think in my um, carelessness, I have replaced a small delta by capital delta. So I think Ryan's wish has been satisfied. Okay, so now the acceleration vector may also, for many purposes, be regarded as a vector. Okay, I will answer the question in the chat box in a moment. So we would like to view the acceleration vector also as a vector emanating from the instantaneous location of the particle. Okay. So just as we said that the velocity vector is to be viewed as the tangent vector to the curve and thought of as emanating from the current location of the particle. Same way, we would like to view the velocity the acceleration vector, which in this case may be pointing some direction like that. We would like to view it as emanating from the instantaneous location of the particle. uh, However, the position vector itself emanates from whatever chosen origin you have. That is our. Okay, now we have a question from Shyam Patankar asking whether the dot on top of x denotes the time derivative. You are indeed correct. I did not say x dot means dx dt. Yes, so the dots are very convenient notation for time derivative for derivatives. X is a function of only one variable, so there is no confusion as to which variable you are differentiating with respect to. And for time derivatives, we particularly are accustomed to using dots. I think this is a notation that goes back to Newton. You can also see why Newton and his contemporaries had to invent calculus. The motion of a particle very naturally leads to all these concepts of infinitesimal differences and difference quotients and thereby derivatives. Okay. The ideas go back even before Newton. I mean, infinitesimal displacements and concepts of that sort go back significantly earlier. Okay. And now we want to look at one example. Any question about this? Okay, I did not mention, but if you want to take one more derivative, you will get an x double dot. So that is second derivative. Yeah, so the number of dots above x denotes the number of derivatives. Okay, let us look at one example, namely that of uniform circular motion, which is commonly encountered and is a useful model for many approximate model for many things we see in everyday life also. Yeah. Okay, I mean, I had some comments from yesterday. I will hold them off for now. Let's proceed with this. So suppose a particle moves counterclockwise on the circle x squared plus y squared equal to L squared of radius L in the xy plane. So it is moving on the circle at a constant angular speed omega radians per second. So it covers omega radians in 1 second uniformly. So going counterclockwise, here, there, and so on. Assuming it starts from the point L comma 0, by that I mean this point, I will have in mind an x-axis and y-axis passing through the origin of the center of the circle. And so this point has x coordinate L and y coordinate 0. So assuming it starts from there, at t equal to 0, its instantaneous location may be given by the Cartesian coordinates x of t is equal to L cosine omega t. Yeah, so this is going to be x of t, y of t. I think you are familiar with this pair of formulae for the x and y components of a point. Yeah, on a circle that subtends an angle. This angle is well, you should tell me, what is this angle at time t?
Omega.
One more chance.
Omega t.
Yeah, that's omega t. So it covers omega radians in 1 second. So if it has a duration of t seconds has elapsed, then the angle covered would be omega t, the angle subtended. Right. So for that reason, this point x of t, y of t has the abscissa or x coordinate L cosine omega t and ordinate or y coordinate L sine omega t. Okay. Any question about that? Fine. Okay. Yeah. Now, sometimes it is convenient to regard this pair of components as forming a vector, as we have been doing frequently now, and call that the position vector of the particle. So boldface R of t, R vector is L cosine omega t x hat plus L sine omega t y hat. Okay, so it's a vector that points radially outwards from the center of the circle. Thus, R of t is the position vector of the particle relative to an origin that is chosen to lie at the center of the circle. So I think all of this hopefully is reasonable to you. Of course, this picture makes it clear. It just repeats what we have already said. This is the vertical height of that point, also called ordinate. And this horizontal distance is called abscissa. Okay, and the radius of the circle is L. Let us play with this formula a little bit and understand it once more. So of course, if I have said that x and y are given by these formulae, then it is clear that x squared plus y squared is L squared, because the sum of squares of cosine and sine is 1. And that holds at all times, not at any one time alone. And furthermore, we see that the motion is counterclockwise. The formula encodes that, because I mean, if you just start at this point and t is 0 and t increases slightly, you will notice that initially x was equal to L and y was 0. But after a small instant of time, x is going to decrease because the cosine will decrease. One moment, somebody at the door. Yeah, so let's come back here. Yeah, so the motion is counterclockwise, which you can check just by inspection, that from as t goes from 0 onwards, the cosine function decreases, so x is going to decrease, and y becomes positive because the sign increases from 0. So it's going upwards. It's not going downwards. Yeah, so it's going upwards, and that's counterclockwise. Now, from this position vector formula, we can compute the velocity vector simply by differentiation. And you will agree with me that if I differentiate L cosine omega t, I'm going to get minus L omega sine omega t x hat. and then L omega cosine omega t y hat. Okay, so we simply x hat and y hat are fixed vectors. Yeah, that's very important. Fixed basis vectors. So when I do differentiate in time, they don't get differentiated. They are fixed. We will very soon talk about vectors that change with time, even basis vectors that change with location and time, but these don't. And therefore, you get this formula for V. Any question about this? So we are ready
How
now.
can basis vectors change with time?
That is if one is crazy enough to want to work with such vectors. Right? So we're going to do it. Just hold on for.
Sir, aren't basis vectors just the origin? Like the origin can always change, right?
Yeah. See. Okay. Since you have asked, so two people have spoken. I think the second is Ryan Hota. Who was the first who asked this very important question?
Ankon.
Onkon Mukherjee. Okay. Yeah. See. X hat and y hat don't change with time. We have kept them fixed. So at present, that is all that matters. Your concern is how can I have a basis vector that itself changes with time? We haven't introduced it yet, so I suggest you wait. But if you are very eager to know, let me suggest the following. Because of my craziness, I want to define a frame which kind of is adapted to the particle's motion. All right, for whatever reason. Yeah, so particle is moving. Yeah, and at its instantaneous location, there is a tangent vector. Right. Suppose I decide that the unit vector along that tangent is going to be one of my basis vectors. For some purpose, that's very convenient. Okay, so I will define that is one of my basis vectors. I will call it, let me call it the.
Yeah, then it will change with time.
Okay,
right?
so Oncon is now satisfied. Okay, and then starting with that, you can then define one more which is perpendicular to that. That again will start changing. All right, so it is entirely possible for such things to happen. Of course, it will make our calculations a little bit more involved, but we will learn how to deal with that quite soon, actually.
But sir, is it changing? It's not changing, right?
Oh, well, it is. Now, who says it is not changing?
With Ryan.
Okay, Ryan disagrees. All right, so no, look. At this point, this vector was pointing this way along the tangent to the curve. Now here,
But you are taking the basis to be the end all be all, right? It is the supreme judge. So it cannot change. Right? Like
no. See, we are now talking about different bases. One a fixed basis, which we like a lot and would like to keep. Yeah. And I would like to stick to that right now. But because I was a little bit impatient, I talked about bases that change with
sorry, sir,
time.
I think I'm disturbing the class. Please continue, I think.
Yeah. So I hope it is clear to you that if one wishes to define a basis, let's just consider particle motion on a plane. Forget about 3 dimensions. Then even on a plane, at this instant, I want this to be my basis. At a next instant, I want something else to be my basis. Yeah. So I think it is evident that since the direction of the particle's motion changes with time, its tangent and normal vectors are going to change with time. And if we want to think of those two vectors as basis vectors, they do change with time. And we need to deal with that if we are desirous of such an arrangement. Is Ryan, are you somewhat
Yes,
satisfied?
I sir, if you please allow me, I will talk at the end of the class.
Okay, fine. All right, fine. Let us now go ahead and calculate the velocity, the magnitude of the velocity. We've already got the velocity vector itself. Yeah. So now the speed of the particle, which we defined as the magnitude of this vector, which is the square root of the dot product of v with itself, can now be computed. If I take v dot v, I will have 4 terms. The x dot y dot, x hat dot y hat is 0, and y hat dot x hat is also 0. So there are only 2 terms left over, namely coming from the square of this and the square of this component. All right. So you will get an L squared omega squared sine squared plus L squared omega squared cos squared. And this comes with an x dot x hat dot x hat, and this comes with a y hat dot y hat, okay, which are both 1. And therefore, you take the square root of this sum and you get L omega. Okay. And furthermore, since we have assumed that the motion is uniform, that is omega is a constant independent of time, it ensures that the speed doesn't change with time. Okay, I mean, the construction encoded this, but we are simply observing it once again. So since omega is constant, the speed of the particle is constant. By this, I mean the linear speed, not angular speed. Omega is the angular speed. So the linear speed now is a constant, and therefore we say that the particle is executing uniform circular motion. Now the particle goes round the circle. Let us just address some more features of this so that we get used to these terms. The particle goes around the circle once in a time given by the distance covered, which is the circumference of the circle, 2 pi L, divided by the speed of the circle. Sorry, speed of the particle. Okay, I hope you will agree with me that the time taken to cover one circuit around the circle is 2 pi L upon the speed, 2 pi L upon V. Now, writing V as L omega and substituting for V over here, you will notice that the L's cancel and you get that the time taken to go around once is 2 pi upon omega. Okay, so this is perhaps a familiar formula to you, that the time period for circular motion, uniform circular motion, is 2 pi upon the angular frequency or angular speed. So the quantity omega is usually referred to as the angular speed, sometimes also called angular frequency, but maybe let us try to stick to angular speed here. Yeah, and it is usually quoted in radians per second. Okay, so alternatively, we can also say that the particle covers 2 pi radians. 2 pi radians is the full circuit in a time 2 pi upon omega. And therefore, the angular speed is the number of radians divided by the time elapsed. So the number of radians were 2 pi and the time elapsed was 2 pi upon omega. So the ratio gives you omega. So we conclude that the angular speed is omega. I'm just restating the same thing in different ways. Okay, any question about this? Okay, now let's go to the next vector of interest. Or okay, before we do that, let me make a comment. We have now determined the velocity vector. We already had the position vector, and we make the pleasant observation that they are perpendicular. So suppose we take the dot product of V and R. Let me do that. Yeah, just to so R vector was cosine comma sine. Yeah, I want to use the shorthand notation. When I write C, I mean cosine omega t. When I write S, I mean sine omega t. The V vector we have already computed. It is written over here. So let us write down its components. They are minus L omega S and L omega C. Okay, I hope you agree with me. These are the components of the velocity vector. Those were the components of the position vector. When I take the dot product, we already showed last time, the dot product is the product of the x components times plus product of the y components. So R dot V is going to give us the formula minus L omega SC plus L omega CS, which is 0. Okay, so we immediately see that the velocity is orthogonal to the position vector. This, what is happening? Okay, I brought my screen back. Any question about that? This is, of course, clear from the picture as well. The radius vector points radially, and for counterclockwise motion, this is the directional velocity vector. So no wonder they are orthogonal. Thus, the velocity vector is tangent to the circle. That is because the motion is along a circle. Now, the acceleration vector is given by the time derivative of velocity. So we just differentiate once more this formula for v, and we are going to get one more omega coming out, sines turning into cosines and cosines turning into minus sines. So here's our vector. Acceleration vector is minus L omega squared cosine omega t x hat minus L omega squared sine omega t y hat. Okay. Now we make a very nice little observation. We recall that the position vector itself was cosine omega t x hat plus sine omega t y hat. And therefore, we notice that the acceleration vector is actually proportional to the position vector. The proportionality factor is a constant given by minus the square of the angular speed. Okay, so acceleration vector is minus omega squared r of t. We notice that the acceleration has a constant magnitude, namely L omega squared. It is easy to make a silly mistake here and say that the magnitude of, this formula says the magnitude of acceleration is equal to omega squared times the magnitude of L, magnitude of R, but the magnitude of R is L because that is the radius of the circle. So that is our magnitude of acceleration. And we also observe that it points radially inwards towards the center of the circle because of this minus sign. Okay, so this latter feature, that is the acceleration pointing inwards, justifies the name centripetal acceleration for A of t. Okay, so the acceleration for, well, in this case, uniform circular motion. Yeah, that's important. We are considering uniform circular motion is centripetal. So as I mentioned last time, the word centripetal is Latin for seeking the center. Petal has to do with the seeking. So it is seeking the center. So this picture hopefully will convey these things to you, and it gives me a chance to introduce yet another fancy word. So this is our radius vector or position vector. This is our velocity vector, which is tangent to the circle given by the time derivative of r. And then, having found those two, we then differentiate the velocity vector and arrive at an acceleration vector, which we just observed points radially inwards. So that is the picture so far. We will say that the velocity vector is tangential to the circle, since we have shown that it's orthogonal to r. Another word for that is azimuthal. This direction that is tangent to a circle is called the azimuthal direction. Okay. I mean, counterclockwise, that is the usual convention, is called the azimuthal direction, whereas this direction, of course, is radially inwards. Okay, so I have introduced the word azimuthal for the tangential direction to a circle pointing counterclockwise. We will use that term several times in the coming days.
Excuse me, sir.
Yes.
Yes, sir. So you said that the direction that is perpendicular to the position vector r is the azimuthal direction when the particle is moving counterclockwise, not clockwise at all. So is there an analogous term for a particle that when the particle actually moves clockwise, or is this just like?
Yeah, no. See, yeah, I wish there was some other term, but see, so for whatever reason, we like to deal with the right-handed coordinate frames. But if you prefer left-handed coordinate frames, you're welcome to use them, and there is even a name for it, namely left-handed coordinate frame. Now, counterclockwise motion, for some conventional reasons, that is, we often formulate things in terms of that. And the word azimuthal has been come to associated with counterclockwise increasing angle around a circle. If you are increasing it in the clockwise direction, I am not aware of a corresponding term. It's just the opposite of the azimuthal direction, you might say. Yeah. Is that your question?
Yes, sir. Yes, sir.
Yeah. So sadly, we don't have another name for that. Okay, that was Somen Singh. Am I right?
Yes, sir.
Okay, good. Okay, so let us continue. As somebody mentioned last time, the time derivative of acceleration, namely a dot, is sometimes called the jerk or the jolt vector. And I leave it as an exercise to you. So, I mean, just the summary so far is that we have R. R is perpendicular to V. And we have now said that A is proportional to R. So A is perpendicular to V. Okay. Acceleration is perpendicular to velocity. You can go one step further and find that A dot or your jerk or jolt vector is itself perpendicular to the acceleration vector. So I encourage you to differentiate and check by computing the dot product that this is 0. Again, this is for uniform circular motion. I want to emphasize it's a special feature of uniform circular motion. Yeah, and I will also invite you to find out the direction of this jolt vector for uniform circular motion. So, all right, I will comment more on this interesting sequence of orthogonalities. They are not a coincidence. Yeah, so I will say a little bit more about that. Okay, any questions so far? Yeah. Now I come back to some things we were talking about yesterday in terms of work. We observe that if there is a radially inward force, like a person tugging at a string with a stone tied at the other end and rotated. Okay, so that is one way in which you can make circular motion occur. Yeah, so this person tugging at the string is responsible for the circular motion. And the force that is acting on the particle is radially inwards in this case, then we will of course notice that that force, the tension in the string, is perpendicular to the the infinitesimal displacement. Yeah, so the picture is familiar. Particle is, the stone is going around this way, so the infinitesimal displacement ds is this way, and the force was that way. Okay, so if such a force is responsible for this motion, then the dot product, this dot product is called the infinitesimal work done by the force in displacing the particle ds. These are all concepts we have already introduced. And thus we see that a radially inward directed force does no work in moving a particle along a circular trajectory uniformly. So along a circular trajectory. Now, of course, needless to say, this is not the case if the motion is due to a force that is tangential to the circle. All right. I mean, circular motion can arise in many ways. I explained one where a person is tugging at a rope, but it could be different. I mean, there is simply some racetrack that is circular and an agent is pushing the particle along the rim of the circle. In that case, the force is actually tangential to the circle and it actually does work. So we need to be careful. We need to answer the question as to, or ask the question, which force is doing this job and does that force do work or not? The nature of the motion alone doesn't determine whether the force does or doesn't do work. Yeah. Okay, so I hope that distinction is evident to you. Okay, so yesterday there was some discussion about Coriolis and Coriolis and centrifugal forces. These are things we have not systematically introduced. We just mentioned them as names, and the discussion was somewhat imprecise. So please don't worry too much about that. Just as a quick remark, I want to say that these concepts of Coriolis and centrifugal forces arise when one views the motion of a particle from a rotating frame, like the frame of a rotating merry-go-round or the earth, these kinds of situations. Yeah, they don't necessarily refer to circular motion of a particle, right? The particle may be moving as it wishes, or as forces make it move, but we are simply viewing it from a rotating frame. Whenever we do that, there is automatically a certain collection of forces that act on the particle or seem to act on the particle. These are called centrifugal and Coriolis forces. And one can ask whether they do work or they do not do work. And the answer to that question partly depends on how the particle is moving, because as we have just seen, the displacement of the particle plays a very important role in determining the work done by a force. So you need to know the force, but you need to know the displacement as well. So it is not entirely clear if we simply say there is some centrifugal force, it must not do work. Yeah, we have to ask the question, where is the particle moving? So that's why I was a little careful yesterday. If one has in mind only some uniform circular motion, then okay, this orthogonality may hold. But one has to ask a more careful question. Particle is moving on the earth. It need not be moving in a circle at all. Yeah. So then the centrifugal force could have some contribution to energies. Okay, and one can ask similar questions about the Coriolis force also. Okay. Okay, with that very limited remark, let me go to slightly more general setup, namely that of non-uniform circular motion. Any question about our uniform circular story? All right. If not, let us see what changes if we consider non-uniform circular motion. Now, we may model non-uniform circular motion of a particle around a circle of radius L via a certain position vector. Okay, so I hope this will not come as a surprise. Generalizing from our previous formula, namely R is equal to L cosine omega t comma sine omega t. Yeah, this omega t came because it was the angle subtended by the particle at time t. Okay.
It was uniform. That is why we could.
Yeah, because it was uniform, we could write omega t. Very correct. Yeah. However, now all we are told is that the particle subtends an angle theta of t at time t. Now, whether that theta of t increases linearly in time or not is not specified to us. In general, it won't. Yeah, if it increases linearly in time, you may write it as some omega t. But let us consider the more general situation where r of t, simply because the particle is still on a circle, can be expressed in this way as L times cosine theta of t comma sine theta of t. So as an ordered pair, or if you wish, as L times cosine theta of t x hat plus sine theta of t y hat. Okay, so I hope you are now comfortable with expressing circular motion in this manner, the position vector of a circularly moving particle in this manner. This is completely general. No assumption made about the speed of the particle. Okay. Now let us see what the consequences are for things like velocity, acceleration, and so on. For convenience, and because it's quite reasonable, let us denote the time derivative of theta. I mean, the rate of change of angle is called the angular speed. Yeah, so that is the name of this quantity. We will denote it omega of t. Okay. That is, of course, motivated by the previous case where d by dt of omega t was simply omega. So omega was called the angular speed. Here we replace omega t time by theta of t. Okay, so the time derivative of the angle will simply be called omega. It is no longer necessarily a constant. It is some function of time, which we'll call the instantaneous angular speed. Now its magnitude, of course, is given by the magnitude of theta dot. The over dot, of course, stands for time derivatives. Now, if the motion is non-uniform, this quantity is no longer a constant. Not a constant. Okay, so now let us compute the velocity of the particle. We proceed through our recipe, simply differentiate this formula using the fact that x hat and y hat are fixed basis vectors. So as before, we are going to get a theta dot coming outside. Yeah, and cosines are replaced by minus signs and sines are replaced by cosines. So here is our velocity vector. It is L theta dot times the ordered pair minus sine theta comma cosine theta. Now, are you with me so far?
Yes, sir.
Okay, great. Sorry, who was that?
Sir Nirja.
Nirjarnath. Okay, great. Thank you very much. So here we are. Notice that the velocity is orthogonal to the position vector. Yeah, so no matter whether it is uniform or non-uniform circular motion, the dot product of these two vectors is 0 because you got a cosine here and a minus sign here, and you got a cosine here and a sine here. So if you take the product and add them up, they cancel out. So I hope that calculation is clear to you. V dot R is 0, even if the motion is not uniform. This is not a surprise to us because we can see geometrically that V always points tangent to the circle because the particle is confined to a circle. And therefore, V must be orthogonal to the position vector. However, in this case, the speed which we can compute, the speed is given by the magnitude of this V vector, and that is simply given by L times magnitude of theta dot, which we are also calling L times omega, or the magnitude of omega. So the speed may vary with time. When I say speed here, I mean the linear speed. Yeah, so I hope you are comfortable with this. There is a concept of linear speed, which is the magnitude of the velocity vector. There is a concept of angular speed, which is the time derivative of the angle, magnitude thereof. So I hope the distinction between these two speeds is evident to you. Okay. So now we proceed to calculate the acceleration, and here there is a little bit of a new feature. So A is given by V dot. So let us differentiate carefully. So V was L theta dot times minus sine theta comma cosine theta. So if I differentiate it, V dot is going to be, there's going to be several terms. Yeah. So we will do this slowly. Maybe it's the first time you're seeing it. So there are two possibilities. The time derivative may hit the coefficient or it may hit the things inside. So I have to consider both cases, both by a certain rule of differentiation. So which is that rule?
Chain rule.
The product rule.
Yeah, so we're going to use the product rule. And that is also called, named after a famous scientist. Who's that? Contemporary of Newton.
Sir Leibniz. Sir.
Yeah, so it's called also the Leibniz rule. Yeah, so this is in some ways the most important rule in differentiation, and gives differentiation its wonderful properties. So let's calculate this carefully. So yeah, so okay, maybe I should have written it in vector notation. So it is going to be L theta dot minus L theta dot sine theta x hat plus L theta dot cos theta y hat. Okay, so if I differentiate V, let me collect all the terms. Minus L theta double dot sine theta x hat, that's the first. Then we get minus L theta dot times another theta dot. I'm differentiating the sine theta. So I'll get a cosine theta x hat. Is that okay? And then I differentiate the second term in V. So that gives us an L theta double dot cosine theta y hat minus L theta dot sine theta y hat. Okay, I have somebody at the door. So please just make sure you understand this formula. Okay, so any question about how we got these 4 terms? All right, so I mean, like somebody asked last time, we are not proving or we are not checking this Leibniz rule that it applies to vectors just as it applies to real functions. Yeah, or we are not checking this distributivity and such things. So those are sort of understood. Okay. So now collecting the terms, by that collecting the terms, I mean collecting the coefficients of x hat, putting them together, and the coefficient of y hats and putting them together, we see that the velocity, time derivative velocity, also known as acceleration, has got 2 contributions. Actually, let's not collect them. Let's just write them as 2 different terms. One that has to do with theta double dot, proportional to theta double dot, and the other that has proportional to theta dot squared. You will notice that these 2 are of theta dot squared type, and these 2 are of theta double dot type. So I hope you will agree with me that the 2 terms are of this sort. I have a minus sine theta here, so that's been written here, and then I have a cosine theta here from those 2 terms, and then these 2 terms contribute to this theta dot squared. Okay, so now let us, we've done the algebra, we've done the differentiation. Now we need to interpret the results. Yeah, so this is where the surprise or the new feature is. We notice that the first term points tangentially, okay, because it points in the same direction as velocity. Yeah, velocity had components minus sine theta, cosine theta, up to some coefficient in front. And that is the case here too. You have minus sine theta, cosine theta. So we notice that there is a part of the acceleration that points along the velocity. Okay, the first term points tangentially to the circle and is called the angular acceleration, okay, because it points in the tangential direction. The second term points in a different direction because it is cosine theta, sine theta, so that is proportional to the radius vector itself, yeah, the position vector itself. So the second term points radially inwards because of this minus sign. Yeah. So we conclude that the acceleration of a particle moving non-uniformly along a circle consists of 2 vectorial parts. One is radially inwards, and so that should be called the centripetal acceleration. Centripetal acceleration. Yeah, previously we talked about centrifugal force. This is not a force, it's an acceleration. So this is centripetal acceleration. And notice here, there is no rotating frame and so on, simply particle moving around a circle. So this concept of centripetal acceleration has nothing to do with viewing things from rotating frames and so on. So not to confuse with such things. Yeah, so there is a centripetal acceleration as well as a angular acceleration. Centripetal acceleration is by calculation, it points inwards, radially inwards. Could you tell me about the angular part? Which way does it point? Can you give any insight into that? So the acceleration, yes, please.
Which one? So one points tangentially and the other inwards, right? Because cos theta sine.
Right, you're quite right.
Yes, cos theta sine theta is basically the coordinates of the particle itself, and negative of that.
Not of the particle's position or location. Okay, yeah, but no, yes, you are quite right. So this part, which I can call the radial acceleration or the centripetal acceleration, points inwards. I'm asking about this one. It is tangential, but tangential leaves 2 options, right? Which is
it is around the velocity.
Very good. Well, okay, in a sense, it depends on velocity, but more precisely, it depends on theta double dot, right? I mean, if the sign of theta double dot is positive, then it would be counterclockwise. And if the sign of theta double dot is negative, it will point clockwise. Yeah, I hope I got those signs right. Do you see what I'm saying?
Yes, sir.
Yes,
Yeah.
sir.
So the point is that the radial part of the acceleration always points inwards, but the angular part of the acceleration, the direction of that is determined up to two possibilities. It could be clockwise, counterclockwise, depending on the details of the motion, depending on the theta double dot expression, whether it's positive or negative. Okay. So all right. Any question about this? Yeah. So we come to the interesting conclusion that the acceleration for a particle moving non-uniformly around a circle is in general neither tangential nor radial. Yeah, it is some combination of the two. You can use your parallelogram to create the actual acceleration vector. That is quite all right. Acceleration does not have to point inwards, can point in some oblique direction. And moreover, the dot product of acceleration with velocity is not zero for non-uniform motion. Yeah. Now, can you tell me how I can take the limit of uniform motion? What will happen to these formulae? How do I reduce to that case? Which terms can I omit?
Sir, terms containing theta double dot.
Very right. Yeah. So, sorry, who was that?
Sir, Kaustubh Manda.
Kaustubh Manda, yes. And you are?
Sir, I'm not on campus.
You're not on campus, yeah. So Kaustubh has rightly pointed out that the limit of uniform motion is obtained simply by putting theta double dot equal to 0. So then you will, the first two terms will go away, or these two terms will go away, and the tangential part of the acceleration is lost. All right. So that was just a nice little example and working with the vectors and the derivatives. Okay. So any question about what we have done here? Yeah. So of course, operationally or calculationally, if somebody gives you a formula for the position of a particle as a function of time, it is straightforward to calculate the velocity and acceleration, these things, simply by differentiation and keeping track of vectors. Okay, but of course, the interpretation is quite important, and that's what we have tried to emphasize here. Okay, so now I just want to make some general comments based on our previous discussion. This is concerning the rotation of vectors. I mean, very briefly, there are many aspects to this issue. Yeah, so let me just recapitulate. What we have observed is that we have observed that the velocity of a uniformly rotating particle is orthogonal to its radius vector, to its position vector measured from the origin placed at the center of the circle. Okay. In other words, the time derivative of the position vector r is perpendicular to r itself. That is, r scalar product with dr dt is 0. This is what we have observed for uniform circular motion. And not only that, it is valid even more generally. It is true even if the rotation is not uniform. Okay. Even for non-uniform circular motion, we observe that r dot v is 0. Okay. That is, r dot is 0. So this is true even for non-uniform motion. Let us comment on the significance of this. Okay. So this is a brief comment on that. So suppose a vector A. By the way, this brief discussion is also covered in the book by Kleppner and Kolenkov. So if you wish, you can have a look there as well. This comment. Suppose A is any vector such that its time derivative is orthogonal to A. Okay, so that we want to expand our setup a little bit. This need not be the position vector, simply some vector associated to particles dynamics. Yeah, but it has the property that it is orthogonal to its time derivative. Okay. So what does this mean geometrically? Let us ask that question. It means that in particular, the infinitesimal change in A in a short duration of time is perpendicular to A and not along A. Okay. So I hope the import of that is clear to you. You have a vector A. After a small instant of time, there is some new vector A of t. This is A of t plus delta t. But if the A dot points this way, right? I mean the rate of change of A. If A dot is perpendicular to A, then in a small instant of time, A will move tangentially, not radially, and therefore the length of the vector A cannot change if this property holds. This means the magnitude of A cannot change. If A scalar product A dot is 0, then the magnitude of A cannot change. In other words, such a vector, if it cannot change its magnitude, can only rotate. That's the only other option. All right. So let us obtain a formula for dA dt, the magnitude thereof, okay, in a simple manner. Let us proceed from first principles. This infinitesimal change in A using a capital delta for a change is defined as A of t plus delta t minus A of t. Okay, so this is the infinitesimal change in the vector A. Now, since the length of the vector A does not change, we will make a small geometric construction. The three vectors, namely A of t plus delta t, and delta A, form an isosceles triangle with delta A as the base. Okay, so let us see this in this picture. This was my initial vector A. It's the final vector A of t plus delta t. This is the change in the vector, points from the initial to the final. So that's called delta A. Since the length did not change, these are two sides equal length. And so this is an isosceles triangle. And let us call the angle at this apex delta theta. So delta theta is the angle of rotation. Okay, now let us estimate the change in A in magnitude. Yeah. Well, it is simply the length of the base of this isosceles triangle, and you will agree with me that it is twice this little length, and that little length is given by A sine delta theta upon 2. Okay, so I'm just using this angle as delta theta upon 2, and using basic trigonometry, you will observe that this opposite side has length hypotenuse times the sine of the angle. Now, for small angles, because these are infinitesimal displacements, we can replace the sine of an angle by the angle itself, yeah, by the leading Taylor approximation, and the twos cancel each other out, and you find that the magnitude of the displacement or the magnitude of the change in vector A is given by the magnitude of A itself times the magnitude of the angle of rotation for small angles. So that was a long story. I hope you are following. Yeah, so as I said, we have used the linear Taylor approximation for the sine function in replacing sine of x by x for small x. Yeah. Now dividing by delta t and taking the limit as delta t goes to 0, we find the magnitude of the rate of change of this vector. It is given by dividing this by delta t and sending delta t to 0. So you will get A times d theta dt. Yeah, so d theta dt, of course, is the angular speed of the vector A. Okay. So we have obtained now a formula for the rate of change of this vector in magnitude in terms of the angular speed of the vector. Now we may apply this calculation to circular motion where A is given by the radius vector itself. Then dA by dt is the velocity vector. Yeah. Then dA by dt is simply the velocity vector and its magnitude is the linear speed of the particle. And what we have then demonstrated is that this linear speed of the particle is given by r times the angular speed of the particle. V is equal to r omega. That's what we have shown by applying it to this case. Yeah, omega d theta by dt is the angular speed of the particle. Okay. Of course, in this discussion, there is no stipulation that either the speed linear or angular be constant. That is not required. Uniform circular motion is just a special case where omega is a constant. Okay, that is the case we studied earlier today. So in other words, we have found that V dot R is 0. Oh, no, I didn't mean to say that. Notice that V dot R is 0 since V points tangentially or azimuthally while R is radial. Okay, so this ensures that the length of R does not change with time. So this was just a geometric interpretation of what we have seen. In the case of uniform circular motion, we have even showed that the acceleration, namely V dot, is equal to minus omega squared R, so that V dot is also perpendicular to V. Yeah. So now using our geometric interpretation, we can then conclude that the velocity vector also cannot change in magnitude with time. Okay, and therefore the V vector must also simply rotate in the case of uniform circular motion. So any vector A whose time derivative is orthogonal to itself necessarily must rotate. Its length cannot change. This is the basic observation we are making.
So you're assuming this is true for all times?
Yeah.
Not only for one particular. Yeah.
Right. We are assuming this is the case for all time. So this is equal to 0 for all t. Indeed. Yeah. So this symbol means for all. So, I mean, if it was valid only at one time, then it will be a local statement about the infinitesimal vicinity of that time. But here we are assuming that this is equal to 0 at all times. And we are simply making an observation that this A vector can be chosen as the radius vector of a particle executing uniform or non-uniform circular motion, or could also be chosen as the velocity vector of a particle executing uniform circular motion. Yeah. So in both of these cases, the corresponding vector A retains its length at all times. And therefore, we see that the velocity vector in uniform circular motion remains of constant magnitude. That magnitude is the constant speed. But in non-uniform circular motion, the velocity vector does not maintain a constant length, and it is not anymore orthogonal to its derivative. Yeah, so we have already observed that V dot A is generally not 0 for non-uniform circular motion. Okay, I went through this a little bit quickly, but let me pause to ask if there's any question.
So the rotation will be circular, not necessary.
I mean, when I say a vector rotates, its tip, the locus of its tip traces out a circle if it's on a plane. Yeah.
Ellipse.
No. In the case of an ellipse, the radius vector doesn't maintain a constant length.
Oh, right. It's
Yeah.
constant.
Yeah. So when we say that this condition holds, it automatically rules out. I mean, this implies that the magnitude of A is maintained in length. I mean, I will discuss this once more, or I'll give a problem concerning it. Yeah, which you can see in another way. So the motion has to be of a rotational sort. Yeah. There is a separate question whether the motion is on a plane or is in a higher dimension. If it is in a higher dimension, it is possible that the motion is not confined to a circle. Yeah, it is still confined to a sphere, but it may not be confined to a circle on that sphere. Okay, so there are such possibilities are there. Okay, and I will leave you to check, verify that not just that the velocity vector doesn't change in magnitude for uniform circular motion, even the acceleration vector doesn't change in magnitude for uniform circular motion. Okay, I mean, we've already derived the formula. You are welcome to check that. Okay, so this sequence of orthogonalities like r dot v equal to 0 and v dot a equal to 0 and a dot equal to 0, yeah, are all applications of this are all instances of this single formula, with the uniform circular motion providing a nice example. Okay, we are out of time now.
Oh, you haven't yet spoken on higher dimensions, right? You
No,
haven't yet.
yeah, we have been speaking in on
Okay,
a plane
okay.
so far. Yeah,
Okay.
I just as a side remark, I said that this formula, scalar product A with A dot equal to 0 can be used in any dimension. It can be applied in 3 dimensions also. It will still apply that the vector A is purely rotated at that instant of time. It is not elongated or shrunk. Okay, so this means that A rotates, does not shrink or elongate. And I think those words apply whether you're in 3 dimensions or 2 dimensions. Yeah, any other question? Okay. If not, since we are out of time, let us stop here. And yes, please.
Sir, I just had one question. Ankan at the beginning of the class had asked a question with regards to why we actually shift the origin when we are considering the velocity vector, but we don't really shift it. I mean, yeah. So why we don't do that? Can you please repeat that once again, because my internet wasn't really working well that time.
Oh,
So
okay. Sure. Yeah. So sure. The point is the following. We were saying that the velocity. So okay. What's the setup? We have an origin, a fixed Cartesian system of x and y, yeah, and a particle moving in this Euclidean space. At the instant t of time t, it is located somewhere. At some other time, it is located elsewhere, and so on. Yeah. Now we have the concept of a velocity vector, which is a tangent to this curve at the instant considered. You will notice that this velocity vector, because it is the tangent to the curve at the instant considered, has an origin located at the current location of the particle. The origin for the velocity vector is not the origin of your erstwhile considered frame. Okay? That is simply some fictitious frame you have set up for your convenience. The velocity vector defines for itself an origin, namely the instantaneous location of the particle. For this reason, it is convenient in discussions of the velocity vector at a given instant to move your convenient frame to that place so that you can resolve this velocity vector along these axes. Okay, so this is the key point. The origin for the velocity vector changes with time, and therefore it is reasonable, if you want to resolve the velocity vector into Cartesian components, you would need to use a frame that moves with the particle so that its origin coincides with the current location of the particle. That is the key point. Is that
yes,
clarified?
Sir.
Okay,
yes, sir.
was that Somendra?
Yes, sir. So when you also spoke about the acceleration vector, then you also stated that it is convention to assume that the acceleration vector is also being applied at that particular point wherever the object is. So doesn't this again harken back to like problem number 5 that we were discussing yesterday? Because had one known that this is the convention, then one could have actually assumed that it is moving radially outwards. But if one doesn't know that is indeed the convention, then you can really resolve it all down to just one plane.
Yeah. Yes, you are. I understand what you're saying. Yes. So we have learned. We have made a lot of progress since when you answered this question in problem 5 over the weekend, and today we have made a lot of progress. We now believe that we would like to view the acceleration vector as emanating from the current location of the particle. Let me give you a deeper physical reason for this, and this goes back to Newton's second law, which relates the acceleration of the particle to the force acting on the particle. So for such an equation or principle to be sensibly written down, they must both act on the particle. So force is acting on the particle. It emanates from the location of the particle. So we would like to view the acceleration vector also as emanating from the current location of the particle. Then we can compare these two vectors and in particular say they are the same or different and so on. Okay, so that is one of the reasons.
Thank you so much, sir. That's been very insightful, sir. Very, very grateful. Thank you.
Okay, thank you. Any other questions?
Sir, can I talk about that basics, changing basis?
Yes, please.
Sir, in changing basis, the fixed basis, you are saying that it is fixed at the ground, right? A particle on the ground.
Okay.
Right. Yeah. So, as far as I know, when we take a changing basis, it is not actually changing because that fixed particle on the ground is changing. That basis is fixed, right?
No. Wait. Let me, okay, you said a few things. I want to clarify a little bit. When I say a fixed frame, I mean one that is fixed to the walls of my room. So the corner is the origin and the vertical upwards along the rim of the door is the z-axis, and along this wall is x and y. Yeah, that is my fixed frame. Now, what is a moving frame? It is one that moves according to some rules. That rule may be that the origin for this moving frame is at the instantaneous location of a Indian hornet or a garden bee that is moving inside my room. Yeah, so that's a moving origin. Now, with respect to the wings of my bee, I may define some 3 axes, and that will become some moving frame. That's what I mean by a moving frame.
Yeah, what I'm trying to say is that with respect to that moving frame, the moving frame is not itself moving, right?
That is quite right. When you relate the moving frame to the fixed frame, that is where the relations arise. The moving frame with respect to moving frame is not moving. You are quite right.
There is no fundamental difference between a moving frame and a fixed frame, right?
So it would seem until you study physics. Yeah, and there is a very deep fact of physics that there are certain frames that are distinguished. Now we have to come to terms with this, and Galileo taught us about this. I am going to discuss that in the coming days.
Okay.
Yeah. So a frame fixed to a bee has some very, very peculiar properties which are not the case as regards frames fixed to the walls of my room. And this was something that was discovered through experimentation with the fishes and bees and balls and so on, and moving in ships and so on. And we will talk about that. So, but in a purely talking about frames without any connection to physics, yeah, they're all equally interesting. Okay, okay. So Ryan and Somendra, I hope you're satisfied. Any other questions? Okay, if not, we will stop here. I wish you a good afternoon. Okay, what's your question?
That question, I mean, that I'm asking that, are you going to take hybrid mode in future?
Yes, I do wish to do that. I need some. Is that Ankon? Your wish will be granted. You please wait a little bit. Meanwhile, I have a question from Shyam Patankar. In non-uniform motion, we denoted omega of t as the time derivative of theta. How did you get that? Good question. Well, I did not get that from somewhere. I defined it that way. So no wonder it was that way. So, but of course, that definition was for good reason. Let me go back to that expression. We simply defined the rate of change of the angle subtended by the particle to be omega. This is a definition. One can't argue with the definition. One can only ask, is the definition a good one or a bad one? We will argue that this definition is good one because it reduces to the constant omega in the case of uniform circular motion. In the case of uniform circular motion, theta of t is simply a linear function, namely omega t, where this omega is nothing to do with that omega a priori. So if I differentiate this, I will simply get omega. So Shyam Patankar, are you with me on this?
Yes, thank you.
Okay, good. Yeah. I hope you are convinced. So this is simply a definition, and I have tried to convince you why it's a good definition. The function omega of t reduces to the constant omega in the case of uniform circular motion, and that is why this definition is motivated. Okay. Any other query?
How far can we use complex numbers?
You can definitely you can use complex numbers even in the problem we have just now discussed. Instead of using x hat and y hat, you can use complex numbers. You can rewrite this position of a particle on a plane as the x component as called the real part and y component as imaginary part, and proceed that way. Of course, concepts like dot products will have certain formulae in terms of complex numbers and complex algebra. You will have to do some translation service. Yeah, so it is quite helpful. There are many problems in physics, planar motion, where complex variables are extremely useful in deeper ways as well, not just as numbers, even as functions, complex functions and their analyticity properties and so on. So,
Can we assume, like, can we just directly use them without any statement of assumption or anything?
No, see, a complex number regarded as an ordered pair is just as good as a Cartesian components of a vector. So to that extent, they are equivalent. The question is, how do operations manifest themselves? Operations like, I mean, the first operation is differentiation in time, and we will say that the imaginary unit doesn't change with time. That is like saying that y hat doesn't change with time. Yeah, so that you take as a axiom. But then you have to rewrite things like dot product of vectors. How is it expressed in terms of the real and imaginary parts of a complex number? You have to get formulae for that. So once you form a dictionary, you can proceed with that.
But what about exponential functions?
Yeah, no. The question is what you want to do. So if the motion of the particle is somehow easily expressed in terms of exponential functions, which may very well be the case, because if you're doing some uniform circular motion, there is some cosine and sine appearing, it is very conceivable that the exponential function forms a more compact notation for that. Then you're very ready to do that, right? After all, try to take some formula e to the power of I theta of t. Yeah, resolve this into real and imaginary parts, and then rewrite that as a vector, and you may discover that this is a simpler notation for this longer formula. So yeah, so you're very welcome to use such things. they are very helpful, but one has to think. Yeah. Okay. Any other question?
So this is not a question with regards to academics. I just wanted to ask if we had another class after this.
Okay. You mean today?
Yes, sir, today.
In which not in classical mechanics. You don't have any other class in classical mechanics today. As far as I know, there is no other in the schedule. There is no other class, but there is an environment course in the afternoon. I don't know the details about that. So please inquire in the office or with our registrar. But we will meet for classical mechanics again on Tuesday, the same Zoom link. The videos for these lectures are put on the website. There is a YouTube channel for it. So Kaustubh, is that what you were asking?
No, I thought we missed a couple of classes this week, so maybe other professors also had extra classes or something.
Yeah, no, to my knowledge, at least I am not aware that they have scheduled it. The one that I have scheduled, I have specifically told you about. So please, if you have not received any email or specific information on that, then it means that it is not there. Please check with your classmates.
Class for
Sorry?
this.
Sorry?
You need information on this extra class for physics for today.
Yeah, only for physics today. Yes.
Yes, sir. Thank you, sir.
Yeah, you're welcome. Okay. Any other questions? Okay. If not, I wish you a good afternoon and have a good lunch when it is lunchtime. We shall be in touch and meet again on Tuesday morning. Okay. And happy Independence Day.